So today we'll be looking at counters, right? And there are various types of counters that we have seen in our day-to-day lives, right? It could be your stopwatches, it can be the traffic light controllers, and it can be many other applications, right? I've just named a few, but then the applications are numerous. Now, if we think of clock, the first thing is, why do we need a clock? Now, as you all know, with the help of clock, things happen in time, right? So if there is no clock, then the processor wouldn't know when to fetch, when to execute, and when to decode, right? These are the main three things that your processor does, right? Fetch, decode, and execute. So if there is no timing, right? So things wouldn't happen as required. So today we'll be looking at few counters, right? Counters, it can be up count, it can be down count, synchronous, right? Asynchronous. You've studied in your previous semesters, right? Exclusively how to design a counter, using VLMORE machines, right? So today we'll be stressing on the synchronous type and asynchronous type of reset. And when we say synchronous, it is associated with the clock. And when we say asynchronous, right, which means we do not see any clock there, right? Which means it just happens randomly, without taking clock into consideration. And then any sequence counters, just randomly, it happens. So we are going to look at these programs today, okay? Right. So to write a Verilog and VHDL code for 4-bit binary and BCD counters, right? So this can be synchronous, asynchronous, and any sequence. So which means we will be looking at 6 programs altogether, including Verilog and VHDL types. Okay, fine. So as usual, the minimum requirement is Xilinx, okay, which is 12.1 and above. Okay, and yeah. In digital logic and computing, a counter is a device which stores and sometimes displays the number of times a particular event or process has occurred, right? So it can be, if you can think of how many people has visited this place, right? There will be those walk-in counters, right? As soon as a person passes through, the counter, jumps, increments to the next level. So they will know approximately in a day how many people are, coming to that particular spot. So counter is one such application wherein a condition is given, right, and based on that condition, the count either increases or decreases. So then it is accordingly classified as up count and down count, right? Okay. So this is often in relationship to a clock, right? So always these counters are associated with clock. How do I say that it's associated with clock? When I say synchronous, asynchronous, right? So it is referring to clock. Binary counters are counters that go through a binary sequence, and an n binary counter is made of n number of flip-flops counting from 0 to 2 raised to n minus 1, right? So which means we are looking at sequences. Say if I say from 0 to 9, then that becomes my decade counter, right? So it's 10 steps. So for each increment, okay, for each increase in the bit, the number of flip-flops increase. Okay, so each flip-flop will take care of 1 bit. So the BCD counters follow a sequence of 10 states. So when I say BCD, binary coded decimal, so it follows 10 states and count using numbers from 0 to 9. Okay, 0 to 9, and then returns back to 0, and then it keeps on repeating. So it's just like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next step is going to be 0, right? So that's how it is. The first one that we will look into is binary counter with synchronous reset. Okay, so Okay, so when I say a binary counter, right, with the synchronous reset, what comes into your mind? There's binary numbers involved, right? And um, there's counting happening, right? And when I say synchronous, then it means that we are looking at referencing it with clock, right? Okay. So as usual, we are going to give the initial declarations, library use, okay, then standard logic, okay, unsigned. So all this we are going to give, right? So now we are going to start with the body, which is entity, okay, and then entity name is port. What all we are going to give in the port. So what is going to be the clock? What is going to be the reset? Is it going to be inputs or is it going to be outputs? So here in this case, it's going to be inputs. Then we need count for that, right? So it's going to be a 4-bit counter, right? So from 4 zeros to 4 ones, right? So that's going to be the maximum, and it's going to be vectored form, right? Why do we say vectored form? Because it's not just 1 bit, but then it's more than 1 bit. Then I can either say end SPC underscore E, or I can just say end entity, right? So that should work fine. Next, we're going to start with the architecture, right? So the architecture here, right? Architecture, then architecture name of entity name is, so you can see that we have made a small differentiation here, where you can see SPC underscore A, so that becomes architecture, okay, underscore E, okay, so that is the engine, right? So we begin, and then in the process we have sensitivity list as reset and clock. Why reset and clock? Because we are dealing with clock exclusively, and there is something called reset. Reset is it goes from 0 to 1 or 1 to 0. So reset, okay, from 0 to 1 specifically. So begin if, okay, now I'm going to state my start my if condition, right? So if the rising edge of the clock, right? So I think all of you know by now what is a rising edge, what is falling edge, right? So all these are very much familiar to you guys, right? So if I can probably draw a clock, a single clock. Okay, so this becomes my rising edge, okay, and the other side, moving from a higher value to a lower value becomes a falling edge, right? So I am interested in the rising edge of the clock. Most of the things, right, most of the programs, most of the logical circuitry works with always the rising edge of the clock than falling edge, right? So it depends how you want to actually program your systems. Do you want to really look at rising edge, or you want to look at the falling edge? So here we are actually looking at the rising edge of the clock, okay, and if reset is equal to 1, now this is going to check the condition. What is the status of reset? So if it is 1, then okay, then count is assigned with 0. Else, okay, else if reset is not 1, okay, if reset is not equal to 1, okay, then the count is going to increase. So you can see that here it is count plus 1, so which means whatever is the count, okay, that is going to be incremented by 1. Okay, fine. So I have started my if here, I'll end if, okay. So there are two ifs here, right? If checking for rising edge of the clock, if reset is equal to 1, okay. So this if will be ended here, and this if will be ended here. I started the process, so I end it, and I have opened the architecture, and my end by, and it is ended here. So you can as I mentioned, you can say here end architecture, or you can use the name of architecture, which is SPC underscore A. Anything is fine. It should work fine with both architecture as well as with entity. Okay. right? Now for a test bench, right, we will be only using this reset. Okay, wait for 100 nanoseconds, and then again we assign 0. So it is toggling between 0 and 1. Okay, and this condition will actually check if reset is equal to 1, then it's like this. Else if reset is 0, then the count is incremented, right? Okay, so now let's move on to the Verilog part. So you are looking at a module, right? And then here give everything input, output is going to be a reg, and always at positive edge of the clock, pause edge, right? These are all keywords, right? Keywords. Begin if reset is equal to 1, then I'm going to give 4 tick B, which means it is 4 bits and it's in binary format B, right? Else, okay, uh, else I will increment the count by 1. So very simple. If you compare the VHDL and Verilog, if you see, right, here you had to take architecture and process statements and if statements and all of those. But here in Verilog, it's very simple. You just write begin if reset is 1. Okay, because already here I've mentioned the positive edge of the clock, right? And calling the library here is not needed, unlike VHDL. In VHDL you have to call IEEE library, right? Unsigned, many other things, right? You have to call 1164 unsigned library IEEE. So here you don't have to do all of those, right? You just call them. You just mention what is going to be your input, what are going to be your outputs, and what kind of clock you're looking at, and your output, is it a single bit or is it a vectored form, right? Okay, so here also the statement is going to be very simple, which is always begin. Okay, clock is given to negation of clock, so which means high low happens after every 20 nanoseconds, right? Then stimulus, the same thing we're going to use here. Unlike VHDL, I'm not going to use nanoseconds. I'm just going to use hash, and any number can be 100, 80, 90, anything for that matter. Okay, right. Now this was with respect to clock, right? We had clock here, and you can see here rising edge of the clock. So now we'll be looking at asynchronous, right? Which means it is not in sync with the clock. It can happen any point of the time. It is not really dependent on the clock, right? So we will see how this works. So library use, okay, we are just calling them all, just like in the C programming you have hash include stdio.h, right? So the header file, standard input output, right? Hash include. So here we are including the files from the library. Okay, yeah. So entity, right, we're just naming it as abc underscore e, and then port, right? All that is given here inside the port, and the count buffer, okay, 3 down to 0, so which means it's going to be a 4-bit. I'll end my entity, then I'm going to start my architecture, right? Entity's name, then I'm going to begin it, okay, process, and as usual reset and clock. Now see here, okay, the importance here is given to reset first, okay, but initially here we had given to clock, right? First only if clock, then you're going to check, but here you're only checking for reset first. Okay, if reset is 1, then count is given 0. Else if rising edge of the clock, okay, then you can, so which means dependency of reset, okay, is not taken with respect to clock. Okay, so the only thing that we're going to check here is reset. So it is like on and off, so the count begins. Okay, count begins. So that's the difference here. It's pretty same, just that you're not including the rising edge of the clock here. Okay, reset is given the higher priority, so which means it's not depending exactly on the clock. So here if reset is 1, okay, then the count is assigned to 0. Else if rising edge of the clock, so which means whenever it is going high, okay, then the count will actually go to next. So this resetting and counting, right, happens um, before the clock, right, before the clock. So we end the if here, which was opened, end process is taken here, and end architecture. Okay. So here you can see, right, reset is given 1 and then wait for 100 nanoseconds, then 0, 1, 0. So it is just like, you are trying to give a toggling value to reset, okay, 1 0 1 0 1 0, right? And whenever there is a 1 0 and all those, right, you can see that in your program here, right, the count is assigned to 0, and it's like reset, right? Reset is ultimately, see, you should understand, when I reset something, whatever is the values there, immediately it will be nullified. Suppose the counter was counting and it came to say 55 or something. As soon as it finds that reset has gone high, which means that 55 which it had counted previously should actually go to 0. Okay, and counting will happen in the next clock, right? So resetting is happening irrespective of the control of uh, the rising edge of the clock, right? So reset has more priority here. Okay, so hence the name asynchronous reset. Okay, so now we'll look at the Verilog part of it, right? Module, okay, abc underscore m, and we'll give input, output register, it's going to be 3 to 0, then always at the positive edge, okay, then begin, and if reset similarly, right, if reset. So I don't have to say if reset is equal to 1, unlike VHDL. I can just say if reset, then count is assigned to 0, okay, so which means it's nullified, it is cleared. And then if the clock is equal to 1, okay, because here I've given us positive edge, right, so the count will go to next. Okay, so similarly here after 20 nanoseconds, okay, the same thing continues. Here it's not given as 20 nano, but then you can just use 20 hash 20, okay, hash 20, and then you can end, and you can add uh, reset is equal to 1 after 100 nanoseconds, then again you can put reset is equal to 0. So this will keep moving on and on. So now if you can see this diagram here, okay, just a moment, right? So if you can see this diagram here, okay, which is actually showing us the waveform, okay, you can see that you know the waveform. Let me probably just maximize it a little. Okay, fine. So this is your clock here going high, low, high, low, high, and low, right? So it is just going on and on. So reset, okay, reset here, whenever it goes from high to low, okay, and this should be in rising edge. This should be in rising edge, and a reset should not be high. So in that case, the count will move to the next value. Okay. So similarly here, say reset is low, okay, and clock is high, so it has moved to the next level. So you can probably think of this like a scale. Let me just put it here, right? It will be easy for you. Okay, so just imagine, right, at this point where I've given in red, okay, so it is actually moving to the next level, isn't it? It is moving to the next level of count. Um, so this is happening when the clock is actually high, so which means it is increasing, it is rising edge, and the reset is, the value of reset is 0. Okay, if the reset is high, then what happens? Whatever count is here, that becomes 0. Okay, that becomes 0. So this will keep counting on and on. See, it came to 1 1 1, and then later it will just go to 0. Why? Because we have taken a 4-bit value, right? So maximum it is going to count between 0 0 and 1 1, and then from 1 1 to 0 0, right? So this is how it happens. So you can actually get the Rtl schematic here, okay, and that is over here towards the left hand side where you have view Rtl schematic. When you double click, you get this, and in fact when you double click on this again, you will find many other logical structures. So I hope up till this point there's no doubts. Okay, now we will look at BCD counter, just like how we had this synchronous and asynchronous reset. Now counter is actually going to increase, and we have a limit here, right? We have a limit here. It is going to count from 0 to 9, and after 9 it goes off to 0. And this is going to be synchronous reset. What do we understand by synchronous reset? It is going to check with clock, and with respect to clock, the reset is happening. It is not independent of clock, right? So we take the program here, right? The VHDL program where we call for libraries, okay, and then we start with the entity, the port selections, right? My clock and reset are taken as inputs, right? And count is taken as a vector 3 down to 0. So which means I'm looking at 4 bits. Right? You see, if I take 3 bits, then the maximum that I can go is still 7, right? I cannot go more than 7. So that's the reason, in order to have 8 and 9, I need 4 bits, right? So I cannot stick with 3 bits. So I will have this 3 down to 0, okay. So once it's 3 down to 0, right, so I can actually count 8, so which means 1 0 0 0, so 8. So 9 means 1 0 0 1. So I am in need of an extra bit here for 8 and 9, so hence I take 4 bits. Then I start architecture, right? Then process, okay. And here the sensitivity list is going to be reset and clock, okay. Then so what do you understand by this sensitivity list being reset and clock? It means that any changes that is happening in reset, any changes that is happening in clock, immediately it will be sensed and it will be it will be acted upon. So that's the beauty of having a sensitivity list, okay. Begin if rising edge. So first we are checking for the rising edge of the clock, okay. So in the rising edge of the clock, then okay, if it is rising edge, then we are checking for reset. If reset is high, then if reset is 1, okay, or count is equal to 1001, then assign count to 0. Now there are two conditions here, right? Why we are taking this condition? Because it cannot go beyond 9, right? I cannot have 10 here because this is a BCD counter, which means 0 to 9. So I have two conditions here. So if reset is 1 and if count, okay, either of the one condition is true, then the count is assigned with 0, okay. Else as usual you keep counting and incrementing. That's the logic. So I end my if here, okay, and for this I end my if here, right? So for this if, it's ended here, and for this if, it's ended here, and the process which I've started ends here, okay, and the architecture ends here, okay. So whatever you have started, you have to end it, right, with respective instructions. Even if there is one end if missing, okay, then it will throw up many errors. You would have seen, just if you rectify one error, okay, so many errors will be actually reduced, right? So because it's all interdependent, right? Okay, so we end the architecture. Now we use here the same thing, reset, okay, is assigned to 1, wait for 100, and then reset you go to 0, right? Fine. So usually the same way that we are going to follow in the Verilog program as well, right? Module, and then the type of inputs, then output is going to be 3:0, 4 bits, then always at positive edge, then begin, okay? If reset is equal to 1, or see, we are not using or, we are using a pipe. So that's how we do it in Verilog programming. So count, it's checking if it is 9, okay, then I'm going to assign it to 0 because it has to come back to 0, right? It will count from 0 till 9, it will count, and then once it is done, okay, it should automatically reroute to the value 0, right? So we need to check, if the value is actually in 9, okay, right? So else then we end the module, and here also we give hash 20, clock is equal to not of clock, so which means high low it happens, right? And we end, and then reset is given 1 and 0 after 100 nanoseconds, right? Okay. So next, the same counter, okay, but here it's going to be asynchronous, which means we are not looking at, we are not prioritizing the clock. We are not first checking for clock, but then first, we just take the reset and continue. Okay, so these are all the same process. Okay, so initially, we're just giving reset. Okay, it's not first being checked with rising edge. Is it rising? Then if my reset is high, no, first only we are just giving, if reset is 1, then count this, else if in the rising edge, okay, if count is this, then you give 0, else if both the conditions are not satisfied, which means I am free to count to the next level, right? So end if, end process, end architecture. So in my stimulus, I will give reset 1 and reset 0 after every 100 nanoseconds. So here in my Verilog program, I'll be looking at the loop. So in the loop, first I'm looking at the reset value, then count is given 0, or if clock, and in the condition, okay, in the count, if it is 9, then I give 0, else then it just keeps going on and on. It keeps continuing the count. My end module. Right? So similarly here, the clock is given high and low values. After 20 nanoseconds, reset is made high and low, right? So two main things here, right? It's looking at high and low resets. Right. Now let us analyze this waveform here, okay, and we'll try and understand how this is happening. Okay, fine. Now you can see here, right? So the reset has gone high, okay, and till the point it's high, it's actually 0. From the time it became 0, okay, from the time it became 0, and with the next rising edge of the clock, okay, so first it is checking for reset. Okay, at this point of time, it's checking for reset. So it was high, so the count is 0. Even though the clock was high, it was not counting, right? So when the reset became low and the clock is high, the count started, right? The count started. So the reset should stay low throughout, okay, so stay low throughout, and it has counted, some numbers have come, and then at this point of time it has gone high, okay, and when it's high again, it gets back to the reset value, okay, the 0 value, to the initial default value. Okay, fine. So here you can take the RTL schematic, okay, and the text schematic as well. Okay, they will be just towards your left hand side, and you can just double click on it. The next one is any sequence. So here we are, previously we just saw it is going in an ascending order, incremental order, 0 1 2 3 4 5. But here any sequence, so I'm just randomly giving 0 8 5 13 7, so which means it should count in this sequence, right? So how do we do it? So we pre-assign the values, simple, right? I just program it, and in such a way that I just give this values beforehand. So I have the library here, okay, and I start the entity. I have my port selections, right? As usual, reset and clock. Majority of the logic remains the same, except the fact that I am going to assign values here. That's it. Okay, that's the extra part, and rest of the things will remain the same. So architecture, then process, I'm going to take clock and reset as sensitivity list, right? Then I'm going to begin, and I'm going to check with the rising edge of the clock. So if it is rising edge, always remember it is a synchronous reset when it's first checking for clock. When priority is given to clock, when priority is not given to clock, then it doesn't become a synchronous reset. It becomes an asynchronous. Asynchronous, which means it's not in sync with the clock. Okay. So I'm going to check with the rising edge of the clock. Then after that, I'm going to check is the reset 1 or 0. If it's 1, then I'm going to assign 0. If not, if with the rising edge and reset is 0, then what I'm going to do is, okay, I'm going to assign some rules. What are those rules? Okay, this is the rule 0 8 5 13 7. Okay, so when it is 0, okay, then I'm going to have this kind of count. Okay, 0, then it makes 8. So after 8, it goes to 5. Okay, 4 5, yeah, 0 8 5. Then it goes to 13. From 5, it goes to 13. So 8 9 10 11 12 and 13. And then from 13, it goes to 7, right? So see, from 13 it goes to 7, right? So from 7 again, I'm getting back to 0. So you can imagine your you know uh, the designing that we did in Mealy and Moray, right? Logic, right? So we had this cycles, right? We had this states, the state diagram. So after 0, okay, it goes to, you can make your state diagram. So here it's going to be 0, and then after 0 it will move to 8, and then after 8 it's going to, so it is like this, right? It is like this. Fine. So I am pre-designing or pre-assigning the values, right? So once all this is done, if any other value is there, okay, so that's when I call when others, then I give a null value 0. Okay, so I'm going to end this case. Okay, I'm going to end this if which I have started, and this if here. So before if I had process, right, and then architecture. So in process and architecture. So reset is given 1 and 0 after 100 nanoseconds. A Verilog program remains to be pretty simple, right? I have clock reset at cloud count as important parameters, and then I define what is my input, what is my output, and am I looking at neg edge or pause edge, right? So begin, and then if reset count, okay, then else, then I'm going to give this same case, okay, 0 8, then after 8 it's coming to 4 5, yeah, it's coming to 5, and then 13 7, and then 0. Okay, so end case, end module. So I'm going to give here 20. So clock is going to go high and low after 20 nanoseconds, and reset is going to go high and low after 100 nanoseconds. So the same count is going to happen here, right? So you can see, okay, after 0, it's not going to 1, but then it's going to 8. So after 8, okay, it's not going to 9, but then it's going to 5, right? So this kind of outputs you'll have to show when the examiner asks you, right? And you may not be able to see this one shot, so you may have to fit screen, right? You have the symbol here, okay, where you can fit to screen, or probably you can use zoom in or zoom out options, to show your output waveforms properly. Okay, so you can get into the RTL schematic, right? The one that you are able to see here, right? So RTL or text schematic, right? Anything asked you should be able to show. So this is the one. See, RTL schematic and text schematic. You just have to double click on that, right? And then you get this kind of window. And then once you again double click on this, you'll be able to find all the logical circuitry, right? So I hope all this explanation was understood by you all, right? So what you can try doing now is try to simulate it, okay, and post in your results. And if any doubts, we will have another meeting, right? Feel free to get back.